Yeah, okay. Let's start today's class. We'll continue with memory interface. In last class, we saw how to interface various RAM and ROM chips to with 8088. Today, we are going to learn how to interface memory chips with 8086 processor. Okay, as we know that 8086 has got 20 address bus. Okay, so 1 MB can be the total memory which can be connected. 1 MB individual 8-bit data can be connected to 8086 address bus. So but they are divided into odd and even banks. For example, an instruction, if you write as move 437ABX, then now it's a word, it's not a byte out here because the register is BX. So we know two consecutive memory locations, that is 0437A and 0437B. Okay, starting with an even, ending with an odd. So two consecutive bytes will be taken. That's how a word will be returned to a memory location. So there are two banks, okay, so that it will enable complete the memory cycle within one cycle. So all the 16, there are 16 data lines, so all of them will be used in one go. Right, so it is divided into 512 KB bytes each memory, odd bank and even bank. Okay, this we learnt in the 8086 architecture. Now the difference between 8088 and 8086 is exactly the same what we discussed. In 8088 and there was only 8 data lines, and all the memory could have been addressed sequentially. Okay, all that 1 MB was addressed. So the designing was pretty simpler. Here it is not complex. You just have to be bit careful because we need to have an even and odd address, right? So the advantage of having even and odd address is that we discussed earlier also. In this enables us to store a byte or a word. Okay, so it is not that the memory doesn't get wasted. So in case I want to store 2 bytes, they can be stored in 2 consecutive memory locations, either even or odd. Or if I want to store a word also, then these two can be considered as a single memory, and a 16-bit data can be stored as a word also. So that is the advantage of having an even and odd address both. And so there will be 2 different chips, so they can be selected so there are 2 different chips, and there are 3 different combinations. One is selecting a byte from the even address, or selecting a byte from the odd address, or selecting a word. So there are 3 different combinations. So for 3 different combinations, you require 2 digital inputs. One is A0, one is BHE. Although here it is just shown for simplification that this chip is selected with A0 and this with BHE, but we know we are going to use a chip select logic to select the appropriate chip out here, right? So this is the chip select logic which we have discussed earlier. If BHE is BHE dash, if you see this is BHE dash, okay, so it is active low. So whenever this is the high bus means the bus from D8 to D16. So whenever the BH is 0 and A is 0, it indicates this the high bus is also selected out here, and A0 is also selected out here. So so that means it is a whole word, it is a word. Okay, so from the 2 consecutive memory locations, starting from the even memory location, that the 16-bit data will be fetched onto the bus bar. Okay, and when BHE is 0 and A0 is 1, that means it is odd. So obviously the even bank will not be enabled out here, but the bus high will be enabled. So you will get a byte from the odd address bus. Okay, so 10 is like if the BHE is not enabled, that means the higher bus is not enabled, only the lower bus is enabled, and 0 indicates that it is an even data, even address. So from address excuse me, so the memory will be the data will be fetched from the even memory bank, and one is generally it's no selection is done out here. Okay, the same thing is shown out here. The only difference here is here for 0 1 and 1 0, right? And although here it is shown as it's not permitted out here, right? Here it is shown as for 1 1 combination. It is shown in 2 cycles. So some of the versions of 80 86, even if you want to get a word starting from an odd address, okay, it can be done in 2 cycles. Okay, in the first cycle, the higher data bus will be brought, because if you write trying to get data from an even address, a word from an even address. Okay, suppose I write the same instruction. Let me go back. The same instruction, if I write 437 B, right? So it is starting from a now and an even address, right? So what happens is starting from an odd address. Then in the first cycle, in the first memory cycle, from the higher bit, because now you can't have can't fetch it in a single clock cycle. Like we have when we discussed the memory organizations, we saw that bit number A0 is used for selection of the chip, and A1 to A19 is given to the both the memory banks, right? In this case, since we are going to start the memory address from an odd number, then the A1 to A19 won't be same for both, for the 2 consecutive numbers. So obviously you will have to use 2 different cycles to fetch the data. Is this aspect clear to all of you? Is there any doubt? Then we can discuss it, right? Because we are starting it with an odd, we are going to say fetch a word starting from an odd number, right? Then suppose odd number like 1, and the next is going to be 2. So the in the address bit, if you see A1 is not going to be the same, right? And both are going to change, and that is the reason you will have to fetch this in 2 different cycles. Okay, so this is done in, it is not 8086, it's not permitted, but some versions of 8086, higher versions, so this is also permitted. If you can write that, it will do it in 2 different cycles. Okay, but let's assume, let's keep it simple. For 8086, this is not permitted. Okay, so now let's take some examples to make things more clear. If memory chips are available, only 2 KB memory chips are available, how do we interface with 8086? Okay, so suppose we want a total 4K memory, okay, and the chip given is 2716. I told so 2716 is an this keeps coming everywhere. This is one of the common ROM switches, so you need to remember that this is an 2 KB memory chip with 8 bytes with 8 bit. Okay, so one byte is the word length out here, the bit length out here. Okay, and total capacity is 2K. Okay, so this 16 stands for 16K bits. Okay, so if I talk in about how many bytes, so you have to divide it by 8, so I get 2K. So this specification 2716 stands for an 2K 1 byte memory. Okay, so you need if you require 4K, okay, and then you require an 8K SRAM. So if this is the problem statement given to us, okay, you require 4K of RAM and 8K of SRAM. Okay, again this 6116 is also an SRAM. Again it is of the same 2K is the memory, each chip, total number of bytes which is 2K, and it is again the width of the this thing 8 bits. Okay, so the memory requirement is, since we require 4K total ROM size, you will have to use 2 such chips, and since we require an 8K RAM, so again the total number of chips required will be 4. So unlike so this is same like 8088, the total requirement will be the same. Only way, the way it is going to be organized is slightly different. So since there are 2 chips, we can we need to organize it as an even and odd, right? Similarly, the 8k, we have to have 2 even and 2 odds, and these 2 even odd combination will give me 4k. Again, one more combination of even odd will give me 4k, and these 4k, these 4k are going to be placed one below the other. Okay, so this is how. Only thing is the organization out here is different than 8088, even odd. So this is the only difference which we have to see. Okay, so this is allocation of the even memory, and this is odd memory. It starts from 000 the memory, then 0002, right? So so for 2k, so since it is 2k, so the total will come FFE, and this is total 4k, right, from here to here, because 2k's we are going to use. This is going to be the odd, so all the odd memories are going to be out here. So from 000 to FFF, this is 4, right? So 12 total 12 bits 1111, right? That is corresponding to 12k, sorry 4k, right? So if you see, these are all the odd memory locations will be there in the odd, and these are all the even memory locations which will be in the even memory bank. Okay, so the same thing can be done for RAM also. You can have 4 different RAMs. These 8 and 9 you can fix it arbitrarily. Okay, because we all, if you see, there are going to be total 3 sets of memories. Okay, within these 2 memories, see within these 2 memories, it will be distinguished with the help of another A0 bit, right? Because even and odd bit. Within these 2 memories, again these 2 will be differentiated, the chip selection will be differentiated by the A0 bit and the BHE lines. Okay, here also. Whereas these 2 in combination, these 2 in combination, and these 2 in combination, there are 3 different sets of memory chips, and they need to be distinguished. So the first 2 bits can be used. They have to be unique, okay, for these 3 sets. Okay, here we have taken 0, 0, 0, 8 and 0, 9. Okay, not necessarily you have to take this way. You can take here 1, 0, 2, 0, 3, 0, anything, whichever you want. But the only thing is they have to be different. They have to be unique. These 3 sets have to have unique MSBs. Okay, they cannot have the same. And not only the MSBs, because there are 3. Okay, at least you will have to use 2 bits to form 3 different unique addresses for these 3 sets of RAMs. Okay, they will be now sets of memories. Okay, even odd together forming 1 set. Okay, is it okay? Is there any doubts? Okay, then okay, so this is the memory interface. Now these are the 3 sets. Okay, now if you see, we have put 0, 0 here. Now this is the starting address and this is the ending address. Now each is 4k, right? So 4k indicates how many bits? 10 bits indicates 1k, right? So 10. Then this will indicate 2k, this will indicate 4k. So from 0000 to 111, this is the entire 4k for the 2 chips together. Okay, from 00, right? 10 is 1k, 10 is from A0 to A9. So this is 1k, 2k and 4k. So this is what from 000 to FFF. Okay, so this is the total for the ROM 1 memory locations, and here we have placed it all zeros out here for the rest of the bits. To this we have given a unique address to this ROM set. And for RAM, again it starts from 000, again it's an 4k. This is again till FFF. The unique address which we have given for this set of RAM is 1000, right? And for RAM 2 we have gone 1001. Okay, so these are so these, if you see these last 4 bits, they are unique for all these 3 sets. So that is how we can distinguish between ROM 1, RAM 1 and ROM 2. How did it become 4k in just 30 bits? 4k is like you require to have, see, 10k 10 bits. Okay, 10 bits till 9 represents 1K of different unique addresses, right? So because A0 to A9, so this represents till 10. If you take, okay, this is the starting address, this is the end address. So if you take this, will A10 to A0, okay, they are 11 bits, so they will become 2K, right? And A0 to A11 is 12 different bits, so they will become 4K. Is it okay, Samrat? Okay, so it is easy to see when we say 16-bit, 14-bit, easy to remember that way, right? And 10 bits, always remember it is 1K, right? So that is A0 to A9. Okay, so this will become 10K, right? Then this will become 1K. Okay, then again you put one more bit, it will become 2K and 4K here. So this is 4K, right? So this is how so these are now 4K memory here, 4K memory here, and 4K memory here, and this we have put unique identities to the three sets. Okay, now for hardware implementation, so we learnt about this LS138 in the last class. So if you have, so we are going to give this has to be given 0 here. So 17, 18, 19 we give it because these are not used. So here for 17, 18, 19 we have used only till 15. 17, 18, 19 these are the address bus. We are going to all zeros are going to generate an 1 out here because it's a NOR gate. So G1 has to be enabled. These have to be given this has to be given permanently 1, and these have to be given permanently zeros for this chip to be enabled. So A3, A13 and A14. A13 and 14 also we have not used, so we are going to put 0 zeros here. So A13, A14. So here in this case we have used an A15 and an A12 as an two different to generate the three different conditions. A12 and A15 is 0 0, 1 0 and 1 1. These are the three different address, right? So we are going to use A12, A15 and an A16. Right, only A12 and A15 have been used, right? A15 and A12. So these are, so A16 is also 0 out here, right? So initially 15 is 0, 12 is 0, then you will get an output. This RAM gets selected, ROM 1, right? 0 0, and then you have a 1 0. Okay, 0 1 is not used here. Sorry, 0 1 is used, not used. 1 0 and then 1 1 have been used here. So this is left idle, so this is used and this is, so the output will be available at ROM 1, RAM 1 and RAM 2 for the three different combinations. Okay, so this is how once you fix these unique addresses. So for you, if a new problem is given to you, if you want to make it things very simple, you can write 0 0, 0 1 and 1 0 also out here. Okay, for this, then it will be straightforward, three outputs from these 0, 1 and 2, right? And then you can use these pins also accordingly. It will be simply 12, 13, 14. So you can use 12, 13, 14 and give rest of the inputs out here. Okay, so this is just shown with a different pin so that you don't get tied up with a sequential input, but you can always do it. Okay, if you want to keep things simple, so you can do it that way also. Okay, 0 0, 0 1 and 1 0, you can use it that way also. Okay, now these three inputs are there, so one of these outputs will go, this is an active low, so one of the outputs will go low, whichever is the desired output. Now the chip select finally also that has to go low. Okay, although it's ROM 1E it is written, this output has to go low. The selected chip has to go low. So if this is selected out here, now if you see, if A0 is low, is even, only then this has to be low. So that is why you have to OR it with A0. Now if A0 is 0, right, and this is also active low, then the ROM 1 will be selected. Okay, now suppose A0 is 1. Okay, if A0 is 1, then this will not, the output will be 1 out here. Okay, so this chip will not be selected. Instead, now if BHE is low, in that case BHE will be low. Okay, if A0 is 1, obviously the BHE also has to be low, so that the even bank gets selected. So you have given BHE into the OR gate, so you have this ROM, the odd 1E stands for the ROM 1 even, 1 O stands for odd. So the odd ROM gets selected out here. Okay, so same way A0 is given to these two RAM inputs also for the even one, and for the odd one the BHE out is given out here. Okay, so this is how the final hardware implementation looks like. Okay, is it clear to all of you? Okay, if you do one or two examples by your own, I think it's there in the tutorial also, then you will be pretty clear. It is pretty simple, these things. Okay, let's take a few more examples. Okay, the same thing is shown here along with the chips out here. So if you see, these are the it's shown instead of 6 chips, the chips are shown out here, 3 and 3. So these are the lower bytes, and these are the higher bytes. Okay, from 0 to the lower data bank and the higher data bank. They're shown as 3 different chips are shown here. So the first 2 sets out here, and they will become the ROM, and then they will become the 2 sets of RAMs, one each from here. Okay, so you have this 0 coming here, okay, to this chip as well as to this chip. So this same circuit here, okay, it is shown out here with these chips like this. So you need to finally draw this diagram also. So you need to do a little bit of practice. Okay, the same, the 74138 is shown here. This is same circuit. Okay, this is expanded out here with the chips also being shown out here. So you need to do a 1 or 2 problems. You need to solve it yourself, so that you are in your exams you will be able to draw this circuit correctly. So if you see the address lines which are given into these chips, all these chips will be from A1 to A11, right? Okay, because each of them are 2K, okay, is the total memory of each of these chips. So the address lines to all these 6 chips will be A1 to A11 out here, right? A0 is being used for chip select, and BHE is also used for chip select out here. Okay. Here this is one more example in which is memory chips are 256 KB memory chips is available. So we need to total memory which is required is 1 MB. So you have 256. Okay, so now for 256 you can have 256 even and odd, and then another 256 even and odd. So that will become total 1 MB, right? So here again this is even and this is odd, this is even and this is odd. So now these two together will form one bank, and this one set, and this will become another set. So we need to distinguish between these two. So we can use the here in this case since only there are 2 sets, we have just used A19 as the most significant bit to distinguish between the 2 sets of the chips. So this we have given 0 and then 1, right? Okay, so and since it is total is 512 KB, so all these bits will be required for, it will be memory from 0000 to 1111 here, and 000 to 11. So this is how the memory interface will be designed out here. So now if you see B and C, and they needs to be completely grounded, and A we have to A we are giving us 19 out here. Okay, and this we are using to enable one of the chips. Okay, either we are going to enable this chip, or we are going to enable this chip here. Here it is slightly different, right? If A is equal to if the most significant bit is going to be 0 out here, right? So here the output will be available here, and it will be available out here. Okay, it will be available if A is equal to 0, it is going to be available here or here, right? So now within that we are going to use to enable this chip, we are going to use A0, and to enable this chip we are going to use BHE dash, right? Okay, so this is a slightly different topology than what we learnt in the earlier. So A0 is the first set of chip which is going to be if 19 is 0, it is going to be the first set of memory chips which have to be selected. So if you see 19 is equal to 0, this will be selected and this line will be selected. Now depending on A0, if A is equal to 0, then the lower bank will be selected. So if A is equal to 0, this chip is going to be selected. So the lower bank, okay, this is the lower bank, okay, this is the even bank. So the even bank is going to be selected. Now if BHE is if A0 is equal to 1 and BHE is going to be 0, in that case the even bank will be selected out here, right? This is the even bank which gets selected here. Now similarly, if A19 is 1, okay, if A19 is 1 and A0 is equal to 0, this will be selected, okay. This chip is going to be activated and this chip is going to be selected, right? And similarly, if A19 is 1 and BHE is 0, then from the even bank this chip is going to be selected. So if you see, this is a slightly different layout than what we saw in the previous example. Is this layout clear to all of you? How we have achieved? See, there are 0 and 1, right? So this 0 and 1 we are using to select one of the sets of memory, right? This is going to be the higher memory addresses, this is going to be the lower memory addresses, right? And then A0 we are going to use to do the even and A0 is equal to 1 for the odd. So this is an even and this is going to be odd, right? So A0 whenever you are selecting, so this even is selected, and BHE is equal to 0, we are going to select the odd banks, okay. Now this is 0, this is 1 out here, so that we are going to select it with the help of an A19, right? When A19 is equal to 1, this for in both the cases the 1 will be selected out here, and if A19 is equal to, the 0 line will be selected out here. So that is how these 4 different chips will be selected. Now coming to one more example, where if memory chips available are 2 KB 4 chips and 4 KB 2 chips, how to interface them, right? So the total 16 KB of RAM is to be, now you have on a 2 KB, this is going to be 8 KB total, and 4 KB chips we have 2 chips, so the total memory is going to be 16 KB. So if you see the 16 KB, so RAM 1, this is going to be an even, so these two together is 2 KB, right, from 0000 to 00FFF. So this is going to be 2 KB 4 KB together, and again we are going to have it says 4 chips are there, so another set again from 00. Now to distinguish it, we have put an 1 out here to make a difference between this and this. So we have put an again this is from FFFE to FFF, so we have put an 1 out here, okay. So and then for the third set of RAMs, okay, it is now 16, this is 8 KB RAM, okay. These are both are 4 KB RAM, okay. So it starts from 3FF, it starts from from 3FFFE, and this is going to end at, the odd is going to end at 03FFF. So if you see this capacity is of 4 KB, right, whereas these are all 2 KB RAMs. So accordingly this location is going to change accordingly, this address bus. So if you see the distribution out here, 0 to 11, okay, because this 2 KB, and this everything we have put as 0 out here, right. In this case again another set 0 to there are 2 KB, so 11 bits, okay, 000 to 11 out here. Now to distinguish between this set and this set, we have changed the MSB and 1 and 0, whereas in this case since it is an 8 KB RAM out here, 4 KB RAM instead of 2 KB, so this is also going to change from 0 to 1, okay. So the total address lines requires an 13 bits, so this is 0, this is 1 out here in this case, right. Now to distinguish between these two banks and this has been put as 1 out here, right. So this is 2 KB you are using an 11 total bits, 000 to 11, right. This is 000 to A11. Okay, and then this we are putting 0 0 out here, 0 1 here to distinguish between these two banks. And in this case, this is 0 and this is 1 because this is 4 KB memory. Right now, instead of 2 KB, so this is starts from it requires total 13 bits. So it starts from 0 here and it is ending till 1, total 1 here. Okay, so this we have put as 1 1 here to distinguish between this bank and these banks. Okay, so this will give these 0 1 0 0 0 1 and 1 0 will give 3 different unique combinations for the 3 different sets of memory. Now, if you see how this is implemented out here is we have taken simple 12 13 12 and 13 are going to these 2 bits we are going to generate to make 3 different combinations, right? So this is 3 different combinations. So if you see 12 and 13, rest 14 is 0 out here, and this is zeros. These are all zeros to enable these chips. So if you see 0 0 0 0 is going to select one chip, 0 1 is going to select the second chip. So that is straightforward. 0 0 is going to make this active low, 0 1 is going to make this active low. Now if you see here, right, 1 0 and 1 1 in this in both these combinations, okay, 0 0 1 0 and 1 1, this chip needs to be this set needs to be selected, right? So this is going to be, you have to take an output from both these both these places and then put an AND gate out here, right? So because if any one of them goes low, the output should be 0. So you have to put an AND gate. So is it clear why you are putting an AND gate out here in this place, right? Because if you see for both these combinations 1 0 and 1 0, this set of memory needs to be selected. So that is the reason why we need to put an AND gate out here, right? This is active low. So even if one of them is 0, so the output has to be 0. So that is why we need to put an AND gate out here and then use the and that is how we generate the 3 sets of chip select. Okay, and within each chip for the first these 2 chips, the address lines will be from A0 to A11 for these 2 RAMs. Okay, it will be A0 to A11, whereas for the third chip, okay, the address lines have to be A0 to A12, right? Because these are one chip will be connected here through an AND gate, and for that you need to have address lines from so that particular diagram is not shown out here, so that you need to make it yourself. So for that chip you require address lines from A0 to A12, right? And then each of them will require a chip select signal which will be generated from here. Okay, is it okay? Okay, so then we the last portion what we are going to see today is 80286. Okay, 80286, the only difference is with respect to 8086, it has got 24 address bus lines. Okay, and rest of the things are exactly same as that of 8086. It has got a 16-bit data bus, and the only thing is the address lines are 24. So since it's 24, total memory size can be 16 MB. Okay, so now one example, we'll take an example of interfacing 4K RAM to 80286. Okay, starting from this address. So if you see till now we were talking out only about 5 hexadecimal numbers for address lines. Now it is going to be 6 because the total address lines out here are 24, right? So that is why this comes as 6 hexadecimal numbers are there. Okay, so available memory chips are only 2716. So this is 2K memory as we know. Now we need to make an 4K. So we have to make it as simple as even and odd number out here, right? So now here it is only shown till 19. Actually it should go till 24 here. So there is an error in this slide. So we need to have till 24 out here. So since it is only on a 2K RAM, so till 11 bits it is going to be 0000 till here, and it is going to come till 1 out here. So this is going to make this is going to be the even, and this is going to be the odd, and this is the least significant bit, that is A0 is going to select the odd and even along with BHE, right? So A0 and BHE. Now here we need to, it's just shown till A18, so we need to have till 24. So again this is missed out here. It is only shown till 18 out here. We need to have the entire set of bits out here, right? So only then we can have this. The only difference which we, with respect to 8086 is instead of everywhere we were speaking about, when we are speaking about 80, if you see here, okay, here 17 to 19. So we need to, whenever we are speaking of 80286, it has to be till 24. Okay, so these bits will be, otherwise the things are same, exactly same as 8086. Okay, so there is one more problem which I will give as assignment. You can try it out for 8K. Okay, the solution is given here. Okay, partial solution is given here. Just try to do it yourself. In case there is you are having any difficulties, you can put a mail to me. I'll provide you the solution through mail. Okay, but I want you to try it out, this one example. Then it will be try to analyze this table, then it will be clear to you. Okay, I have put more of these kind of problems in the tutorials also. So the next tutorial is again based on only on a memory interfacing, starting tomorrow, right? Tomorrow's tutorial. So you will get to solve few more problems on memory organization, so that will make your concepts further clear. Okay, so if you have any doubts, you can ask me now, or we'll finish the class for today. Okay, thanks a lot.